All right, so fundamental theorem of calculus. Sounds super scary and stressful. Anything with the word theorem just makes you like, theorems. Hey, theorems are just the mathematical rules, mathematical things that are true. Hey, they have been proven. Isaac Newton proved that this was going to be true. We're not proving this at all. We're looking at some examples to kind of show that it works. But basically, we're going to go with, you know, Isaac Newton. Pretty much trust him, having gotten calculus right a long time ago. So here's what the fundamental theorem of calculus says. If we're looking to make this calculation, okay, which we know is supposed to be an area. It's supposed to be an area between f of x and x-axis from x equals a to x equals b, which, you know, depending on what my function looks like, x equals a, x equals b, so kind of like that. Okay. Doing that area calculation does not require us to use geometry, because there is a connection between the geometry approach, which would be a Riemann with a lot of rectangles, and the calculus concept of the antiderivative. Isaac Newton is the one that sort of realized that connection was there, or felt like that connection should be there, and then proved it. And how we write this is we say we're going to calculate the value of that integral by taking big F of big F of B minus big F of A. And the big sort of catch trick on that is big F is the antiderivative of little f. Something we previously would have had to do just with geometry. We wouldn't have had either geometry because it works nicely, or geometry that doesn't really work nicely, but we can squish a bunch of rectangles in there and get a really, really good estimation. Okay, Isaac Newton determined for us that the connection between how we do the calculation, he actually did use some geometry to kind of prove why this works. But the trick of the whole matter is writing the antiderivative. Okay? So we're going to calculate things like this without having to draw them, without having to draw rectangles in, without having to run a bunch of Riemann stuff. We're going to calculate values of integrals using Newton's fundamental theorem of calculus, or FTC as we like to call it. Okay. So FTC, step 1, find the antiderivative of little f. Step 2, plug in B and A into that new big F. Step 3, subtract those. Okay. So let's start with this example to kind of get us warmed up. Okay, we're going to do the integral from 2 to 3 of 4 plus x dx. Okay. Now, because I'm annoying, I can't just do this one way. We gotta like look at it. So let me get some Desmos. Let me move this out of the way. Okay. So y equals 4 plus x. So that's just a nice straight line. And so if we were doing the area between 2 and 3 using geometry, let's say, you know, we're not thinking calculus, we're just thinking geometry. So 4 plus x equals 2, x equals 3. In the geometry world, we would hit this with a trapezoid formula. We'd say, okay, 1/2 the height, since when we do this kind of problem, a lot of times the trapezoids are on their side. The height of the trapezoid from 2 to 3 is 1. The bases, well, this side is 6 units, and this side is 7 units. So 6 plus 7. And that's 13 over 2, or 6.5. Okay. Not tough. I mean, as long as you know the formula for a trapezoid, that's pretty standard, straightforward. Area of that trapezoid is 6.5. Okay. Based on Isaac Newton's theories, that's not the only way to get that. Okay. Isaac Newton says we can do that this way. First thing I'm going to do is I'm just going to take the antiderivative of 4 plus x. I'm going to use my backward power rule. X to the n becomes x to the n plus 1 over n plus 1 plus c. So constant 4 in terms of x becomes 4x. X becomes x squared over 2. Now, when we're doing fundamental theorem problems, a lot of times we don't write the plus c because it is going to just subtract away when we get to the very end of the problem. So you'll see me totally get lazy about that. It's amazing I'm still writing the plus c right now. You can absolutely write it, but just know that when you get to the end of this problem and your answer is like, well, hopefully it's going to be 6.5, but it's a number. It's not going to be a number plus c. The c's will, if you keep them in the problem as you do the substitutions, will subtract away. Okay, so that's my big F. So big F of 3 means, let's plug 3 in, and big F of 2 means I plug 2 in. Okay. Now, can this part be tedious? Absolutely. The more complicated the derivative function is in the original integral, the more complicated the antiderivative is, so the more stuff you got to plug in and the messier it is. But we do have a calculator, so even though it's a little like, ugh, you know, we can roll our eyes a little bit, but we can't roll our eyes as much as we would if we didn't have even a calculator to use. So 4 times 3 plus 3 squared over 2, 4 times 2 plus 2 squared over 2. I should be able to crunch those out. Crunchy, crunchy with my calculator. And I'm cheating somewhat so I don't make any more mistakes today. This is going to end up being 16.5 plus c. Okay. Because this is 12. And this is 9 over 2, which is 4.5. So if we did decimals here, 16.5 plus c. This ends up being 8 plus 4 over 2, which is 2. So that's going to be 10 plus c. And so when I subtract those, and I'm writing tons of steps here. I may not write all these steps every time I do a problem. My 16.5 plus c, my 10 plus c, I subtract. This c, you're going to get, just so we get the algebra straight, will be subtracting the 10 and subtracting the c. That's why the c's will cancel. You can trust me on that, so you don't ever have to really worry about them. You can just kind of like pretend they're not there. Once you start plugging things into the big F, just forget about the c. Just like we said. Yeah, it sucked yesterday because I was doing that whole thing and at the very end I made a mistake and then it didn't match and it was like very anticlimactic. It's much more fun when it matches. Okay. Makes my point a lot better when I actually get what I said I was going to get. Okay, so where's geometry? Check. Fundamental theorem? Check. And the fun thing is, this doesn't just work for ones that have nice geometry. This works for crappy geometry. This works for hard geometry. This works for, I can't even really use geometry other than a bunch of Riemann rectangles smushed under the curve to get my best estimate. This works all the time. It's not necessarily the technique you would use every time. You might, on a problem like this, decide that you want to think about it graphically, and that's fine. But it is a technique that works all the time. So even though it may not, you might be thinking in your head, like, well, I don't want to do it that way. I would rather just do the graph. That's fine. If it's a problem that works with just a graph and just a geometry, there's nothing wrong with that. We did a whole bunch of problems like that starting off because all of those problems, geometry was our friend because we had nice triangles and straight lines, so we could make rectangles, and we kind of did everything in a nice way. When it's not so nice, when it's curvy, that's when the fundamental theorem comes into its own, because back in the day, doing a bunch of Riemann calculations wasn't as easy as just typing it into a program. So doing a bunch of Riemann calculations to get an area was a lot more work. Once Newton figured out we could do this using fundamental theorem, it was a huge step forward. Okay. So that's the basics of the fundamental theorem. Every time we do a fundamental theorem problem, these are the things that are going to happen. Antiderivative, plug in top number, plug in bottom number, subtract. Every time. Even when the functions are crazy, even when the numbers are negative, even when things look like they're going to be backwards, even when it might be a negative area. All of those things we had to worry about a little bit more when we were looking at the graph problems. We're literally not going to have to worry about them. Fundamental theorem will take care of all of them. Okay. So that was what I was thinking today, is we would do a couple sort of weird things, which means when I think weird things, I think, you know, negative exponents and negative numbers and fractional exponents and things that are backward. I think I've got, let's see, if we do this one next, maybe we'll do this one next. So we can do 1, 2, yeah, we're going to do probably 4 more if I look at all the different things we want to talk about. Okay. So let's go ahead and try a second one. Okay. I want you to try this one a little bit more on your own. Okay. So we're going to integrate from 1 to 3, and we're going to do the area under 6x squared dx. All right, so see if you can use fundamental theorem to calculate that area.